Let me just quickly check if you're good to go. All right, I think we are up on YouTube as well. Very well. Hi everyone. Hello. Um, just give me another minute. I'll just see if everything's all right on all ends. Then we'll just quickly start. I'll just grab my pencil as well. I think everyone's good on YouTube as well. Ashutosh, if you want to join on YouTube, the channel will be Learn Competitive Programming with CodeChef. We are streaming on YouTube as well, all right? Perfect. I think we're good to go, right? I think we're good to go. Let's just quickly start. Right. Perfect. Okay, I'll just quickly start with introducing myself. Many of you must have been attending the classes previously as well. For those of you who have today as your first class, my name is Riya Bansal. I am currently working as a software engineer at Flipkart, and I have worked many other companies as well in the past, such as Amazon, American Express, and many other companies like that. What we are going through today is like a micro course, right? This was a 3 session course on graphs. All right, and we have already done 2 classes already, in which in the first class we covered the very basics of graphs and how exactly does a graph look like as a data structure. In the second class we actually solved a few problems. We actually learned how exactly we do graph traversals and how exactly go to each and every node and every other edge to the graphs, and we did some problem solving as well, followed by some few implementations in graph data structure, right? I also suggested you to watch 2 other lectures, which you can find on the Unacademy platform as well as on YouTube, which were based specifically on problem solving. It was basically 2 classes in which we did a lot of grid problems on graphs, right? So if you've not watched those videos already, I would suggest after this class you can definitely just go ahead and watch those classes. It will give you a lot of idea about what are the problems which can be solved using graphs, right? So that was the purpose. So today we have the third and the last class on this small micro course on graphs. In today's class, we are again going to cover a lot of concepts. More important would be from the perspective of theory, right? I'll be covering about shortest path. I'll be covering a few shortest path algorithms as well. I'll try to explain those concepts in as much detail as I want, and also we'll be writing a pseudocode for that particular algorithms, right? So we'll not write the exact full detail implementation, because depending on the language the implementation can vary a lot, right? We'll be here focusing on writing, I would say we'll be focusing basically on understanding the whole algorithm, how exactly does that work, and what is the underlying idea about that algorithm, right? So that will be the whole purpose. One thing that I just expect from all of you throughout the class is, if while learning a concept, if that particular concept makes sense to you, you must have a thumbs up emoji in your chat, and please make use of that emoji. That will help me to understand that a concept is clear to you. So let's say if 50 people are attending a class, and let's say 48 students gives a thumbs up, that basically helps me acknowledge the fact that the concept is clear to you and we can move forward, right? So for today's class, you can just sit back, listen. I'll be helping you throughout all the concept. I'll try to build a theory and a story around it so that we can jump from one concept to another concept, right? I'll try to keep it in a good flow so that everything makes sense at each and every point, correct? Can just everyone give me a thumbs up at this point? And I think after that we'll be good to go and we will start the class. All right, perfect. Let me share my screen quickly with all of you. Let me know if the screen is visible to you or not. Can everyone see the screen? I hope whatever I'm writing is visible. All right, perfect. So although we did touch this concept, I believe, in the last class already, but we'll just go through that concept once again, and we'll cover it in a little bit more detail today as well, right? So the first concept, and I would say a very important one, would be to detect cycles. Right? So what exactly happens is, the part for detecting cycles in a graph, we'll cover it in two different scenarios. One scenario I would say would be for the case of, let's say, directed graph, right? And then we will cover it for undirected graphs as well. Right? So what happens in case of a directed graph is, let's say the graph that has been given to me looks somewhat like this: A, B, C, D, right? So I have a node from A to B, and I have an edge from B to C, and I have A to C, right? I have this, I have this, and I have this, right? So the concept is, the concept that I would want you to learn along with some definitions here would be that what we can say is, there is a cycle, there is a cycle in a graph, right? If and only if there is a back edge. So the condition for having cycles in a graph would be that there should be a back edge. Now what exactly is a back edge? I'll just quickly explain that to you. Before that, what I'll just say is, I'll not be able to see doubts continuously, right? So while I'm writing, I cannot look at the screen and take doubts. What I'll do is, I'll look at the screen about every, let's say, 5 minutes or 10 minutes, and then I'll take up the doubts on both the Unacademy and the YouTube platform as well, right? Just something that I wanted to put out there. Perfect. So the condition is that a cycle can exist in a graph only when there is a back edge. Now what exactly is a back edge? I can say back edge is an edge, right? Back edge in an edge that is formed from a node to itself, right? Or a node to one of its ancestors, right? Now how does that concept work is, here you will see that for the node D there is a edge that is pointing to itself, right? So this is going to be called a back edge, right? And in cases of back edge in itself, I can simply say that yes, I can say if there is a back edge, that means a cycle is present. Another case that you will see here is that there is A, there is B, and there is C. Now A is pointing to B, right? And B is pointing to C. Now here you will see that the node C is pointing to one of its ancestors, correct? That means here I can say that A is first pointing to B, then B is pointing to C, and C is pointing back to one of its ancestors. So for both of these scenarios, I can say that a cycle is present in a graph, right? If you want to take a quick example here, we can do that as well. Let's say I have a graph that looks like this. So please note here that we are covering the concept of a directed graph, right? All the graphs that I show here would be directed. We will cover the concept of how it works for I would say undirected graphs as well. So 0, 1, 2 and 3. Let's say this is the nodes and these are the edges, right? And so in order to detect, I would say the adjacency list is going to look somewhat like this. If you remember the graph representations, you will just see how adjacency list works. So for all nodes, I'm simply keeping the information of where exactly is it pointing, right? So this is the adjacency list, how it is actually going to look like. Now what you can do here quickly is you can apply a DFS, right? You can apply depth first search here, and then you can try to find the answer. And how exactly does that work is, we know that to basically apply DFS, we need a stack kind of a data structure. So we have a stack here, right? And we also know that DFS can be applied from literally any point you want. So let's say I am starting with 0. So what exactly will happen is, I will first add 0, right? Then I will remove 0 and I will add its neighbors. And what are its neighbors? 1, 2. So I add 1 and I add 2, right? And also I have a visited array as well. So this is the visited array, 0, 1, 2, 3. So once you have visited a node, you simply put a true at that particular point of time. Now I have come to 2, right? I have come to 2. Now I remove an element from the stack, that is 2, mark it as visited, and I add its neighbors. Now for 2, its neighbors are 0 and 3, correct? So now what you will see is, when you add 3, that is perfectly fine, right? But when you will add 0, what you are going to see here is that it has been already visited. So when you are visiting a node that has already been visited, that basically means that either you came across a backedge in the sense that the node is pointing to itself, or you simply started pointing to one of your ancestors, correct? And this ancestor property works here because 0 was pointing to 2 and now 2 is again pointing to 0. So this is the case how you can detect cycles in a directed graph. You can simply apply DFS the very normal way that you already do. You keep a visited array, and if at any particular point of time you see that you are going to a node which has been already visited, we can simply say that yes, that graph has a cycle because of a backedge. Now is this clear to everyone? How exactly is this concept working? Again, I am going to repeat here that we are talking about I would say directed graphs here. For how many people does that make sense? Alright, perfect. So if this makes sense, let's now move to undirected graphs. Alright, and what I want you to tell me first before moving forward is, if I am going to solve it for a scenario where we are talking about detect cycle in an undirected graph, right, where we are talking about this scenario, do you think the same approach that we discussed above will work for undirected graphs? The same approach of just using a DFS and solving the problem, do you think will that work? The question here is the same logic valid here also? Alright, Abe has a valid point. What about others? What do you think? If I have to detect cycles in an undirected graph, will the same logic of simply applying DFS, traversing all the nodes and marking a node as visited will work here? Alright, let's discuss. what will be the overall idea, if that approach will work or not, right? Let's take an example. What I can tell you is the answer to this will be no, that the same approach cannot work. We need a different way to actually solve that scenario of an detecting cycle in an undirected graph. Let's take an example for that as well. So I have 0, 1, I have 2. So this is an undirected graph. Right, so this is like the graph that is given to us. If I have to draw the adjacency list for this, this is how it will look like. Right, so we know that this is how the adjacency list is going to look like. Right, now what will happen is, let's say I have to detect cycles. So what you will do is, let's say I started with this node, right? I started with this node. If you will apply simply DFS at this point now, what you will do is, you have the visited array, and here it is 0, 1, 2, 3, 4, right? And let's say you have a stack also. So if we go by the previous approach, you will add 1, right? You will simply add 1 here, right? That is the first node. Now you will take it out and you will add its neighbors. Now when you add its neighbors, you add 2 and you add 0, and also this is visited, right? Now what will simply happen is, you take out 2, right? You take out 0 from here, you mark it as visited, and you try to add its neighbors, right? So its neighbors will be 0 and 2, right? 0 and 2, and you will simply say that a cycle has been detected, correct? Because you were at 0 here and now you went back to 1. But actually this was not the case, right? The cycle actually became because of this scenario, right? But what you simply said was that simply since you are going back, that is a case of detecting cycles. Let's start from another node also. That will make the example a little bit more clear, I believe. एक काम करते हैं, let's not start with this node, let's start with some other node. Let's say I start with 3 here. Now what will happen is, you have 3, right? You started your DFS traversal from 3. Now you removed 3 and you added its neighbors, that is 0 and 4, right? Now you have also visited 3 as well. Now when you will take 4, you will take it out, you will mark it as visited, and you will try to add its neighbors, and its neighbor is 3. Now what you saw was 3 was already visited, so you concluded that the cycle was present. But is it true? Is it really true? Was the cycle actually present at this point? We simply had 3 and then we came back to 3 from this node 4. That was actually not the case of cycles being presented. I hope that is the point that everyone should agree, right? The cycle was actually not present at this point, but our DFS approach actually concluded that it was present, right? So what do we do to solve problems like this is, we try to keep track of the parent node as well, right? How exactly do we solve this problem? Right? Here we keep track of parent also, right? So what exactly happened at this particular point will be that, let's say first, this is the node I am starting the traversal from, right? This is the node I start the traversal from, so 0, right? And this is the parent. So a pair I have made is node and its parent value. So currently for 0, if I am starting the traversal from here, there will be no parent node, right? So simply the parent value will be -1. Yes, Jaideep, I am taking comments from YouTube as well, right? If you have any doubts, please feel free to put it in the chat. Right, so now what exactly will happen is, from 0 I have multiple options present, right? From 0 either I can go to 1 or 2 or 3, right? So here I can go to 1, and from 0 I can go to 1, I can go to 2, and I can go to 3, right? So let's say first I pick 1 here. So for this node, the node here currently is 1 and the parent value is going to be 0, right? Since we are, let's say, calling the DFS procedure, I am simply going to pick a neighbor, that was this neighbor, and start reversing in its direction, right? So when I have 1 comma 0 here, 1 is the node. Again from 1 I have two options, either I can go to 0 or I can go to 2, right? Let's say I had two options here, either I can go to 0 or I can go to 2, right? So first option that I picked was that I went to 0, right? So now what you will see here is the observation will be that whatever you see in the visited array, right? So here, since I had already visited 0, so 0 was marked true. Now I visited 1, so 1 is also marked true. Now you will see here that in the visited array, 0 is already visited, right? That means this node is already visited, right? This node is already visited, and I can say at this particular point that this node, right, and 0 is also a parent, right? So if that scenario happens, you will simply move back, and you can say that it is not a case of cycle as well, right? So now what you will do is you will move in the direction of 2. So you have done 0, right? You have done 1. You tried coming back to 0, but that case is not possible, and that is not a case of cycle as well. Now from 1 you had another option of going to 2, so you picked that option now. So when you picked that option, what we can say at this particular point is that the node now is 2 and the parent is 1, right? So please make sure you understand that we are keeping track of the ancestors as well, right? So now when we are at 2, I have two options here as well. Either I can go to 0 or I can go to 1. That means either I can go to 0 or I can go to 1. Now what you will see here is when I pick this node first and I go to 0, you see the observation will be that again V0 is already visited, right? V0 is already visited and 0 is not a parent. So that means we are not in this case that 1 to 2 and 2 to 1, correct? Because we checked initially that the parent for 2 is 1, right? That means we are not coming into this case, and this is a case that the node is already visited and that node is not a parent also. That cycle is found. So that will be the case. So if we have to check cycles in an undirected graph, two conditions have to be satisfied. First, the node should be already visited, and second, that node should not be a parent, right? Because if it is a parent, then most likely the case is that you were at 1, you went to 2, and now you are coming back to 1, right? So if that is the case, I can simply say that the cycle is detected. Is this clear to all of you? In the previous example, what I said was simply you just have to check if the node is visited or not. If that was the case in directed graph, that information was sufficient to tell if a cycle is present or not. But in this particular case, you also have to make sure that that particular node is not parent, and also it's visited as well. Clear to everyone? Abhishek says, ma'am, what is 0 was not present, was visited, but it was not a parent? Abhishek, I think we discussed that case here only, right? For, if you will see here, for 2 comma 1, right, V0 is already visited, right, and it is not a parent also. In those cases, we simply say that a cycle is detected. Correct? I hope that makes sense to each and everyone. Perfect, right? Okay. So that is the case. Let's just quickly go ahead and write the pseudocode for this as well, of how exactly you will implement it. The implementation, I would say, is a basic DFS only, just a small difference that we will make here. I will write the implementation and then you can probably convert it into any language you want. Ismail says, what if there was an edge from 1 to 0? Ismail, there is an edge from 1 to 0. You can see here that the edge is present, right? So the concept here is very easy. Let's say this is the main function that I have, right? Now what exactly will happen is there might be a case of disconnected graph as well, right? Let's say this was the graph, right? So let's say this is the graph, correct? So there might be a case that the cycle is not present in this part, but the cycle is present in this part, right? So you will have to go to each and every connected component. So what I will do for that is I will go to each and every node, right? All the vertices. This simply means that I am iterating all the vertices, and if that node is not already visited, if from the visited part, if this is not visited, then I simply start a DFS from that node, right? And if I will call the is cyclic function from there, I'll pass that node, I will pass the visited array also, and for this node the parent is -1, correct? And if this function returns true, that means there was a I would say a cyclic component, then I am simply going to return true at this particular point of time, right? So that will be the whole scenario. This will be the following. Now let's quickly see how this is cyclic function will look like, right? So I have boolean. This functions basically check that for a particular traversal is there a cycle or not. So we pass the particular node, we pass the visited array, and we also pass the parent, right? So this is the node from which the DFS is starting. All right, so now first, if a node is being visited, so you mark visited equal to true for that node, right? Now you go to all its neighbors, right? This is what we used to do. We used to go to all its neighbors and go to each and every neighbor one by one. So that is the case here. We go to each and every neighbor for all W in the adjacency list of V, right? So we are basically going to each and every neighbor like this. Now if that neighbor is not visited, so there can be two cases, right? That for a particular neighbor it is visited or it is not visited. So if that neighbor is not visited, that will be one case. Else if that neighbor is visited, right? So that will be another case which we will write here, right? So I can say that if that neighbor is not visited, so I will simply call this function recursively again, right? And I will pass that neighbor. Now I will pass the visited array also, and now the parent will be this node V, right? Because the parent will change. Now if this function returns true for a particular neighbor, I will return true, right? So that is the case, but this was the case when the neighbor was not visited, right? Now the else case would be that the neighbor has been visited, right? The neighbor has been visited, and for that neighbor W, right, it is not equal to its parent, right? The neighbor that you just came across is visited and it is not equal to its parent. So this is the case where we can simply say that you return true, because that is the case of cycle being present. In all the other cases, right, in all the other cases we will simply return a false. Just quickly have a look here if this whole pseudocode makes sense. If there's any doubt at any line of code, you can go ahead and ask. If it is clear, right, if the whole concept makes sense, just give a thumbs up, then we will move forward. You can write this down as well if you want a quick minute. It will be very helpful for your understanding in future as well. Clear to everyone, kya? Okay, I'll just quickly show the screen. You can note it down if you want, and then let me know, we'll move forward. Clear to everyone? Did everyone get enough time to write it down? Okay, fine. Quickly take a minute more, then we'll start. All right, perfect. Let's move ahead. Ismail, that can also be done very easily, right? So when you put, I would say, 0 in the stack, right, and when you try to get its neighbors, 0 will come again, right? What we usually do in a DFS scenario is we take a particular node, we take it out, and then we add its neighbors. So when you add 0 to the stack and when you remove it and add its neighbors, 0 will come again, right? And 0 would have already been visited, right? And that will be the case when we can say the cycle is present. So you can do that similarly as well. So if there's a back edge, right, if 0 is pointing again to 0, then the parent for 0 is also 0 itself. So that can also be the case that we can understand here. All right, perfect. Let's move ahead, right? This was what I wanted to put forward once for the concept of, detecting cycle in case of both, I would say, directed graphs and undirected graphs, right? Now we'll move on to another very, very important concept, and that will be shortest path. We'll learn about shortest path in the most simplest manner first, right? And then we will learn how exactly we can do it in different scenarios, right? How will that concept actually work? So if you remember what we discussed in the previous class for the concept of BFS, right? If you remember the graph, I'll just show it once again as well. Right, so this was the graph that is present to us, right? Now what exactly happens is, we saw that if we do a BFS kind of a traversal, if we do a breadth first kind of a traversal, we know that in breadth first search we do a level ordered kind of a traversal, where each node is assumed to be present at the level, and the node from which we start BFS is considered at the level 0. So this is essentially at level 0, right? And I can say these nodes are present at level 1. right? I can say this and this, all of them are at level 2, and the concept similarly goes on. And what we concluded from there was, if there is let's say a particular level x, that basically means that all those nodes on that level are x edges away from the source, right? Those nodes are x level away from those nodes. So when I say on level 2 these 4, 3, 6 and are present, that means they are at a distance of 2 from the source node. You can see here as well, just to confirm it. So for 4 I can have this, right, that is 2 edges, and for 3 also you can see that this and this edge, right? And for 6 also you can see that this edge and this edge, right? So that part was concluded here, right? I can say that if simply 0 is at the root and if 1 and 2 are at level 1, I can simply say that their shortest distance from the root is 1. That means all these nodes 4, 3, 6, their shortest distance from the root here 0 is going to be 2, correct? And that is defined by the level on which they are. So what we concluded here from this was that BFS can be used to find shortest path between two nodes in a unweighted graph. Now the important part here that I would point here is that what you saw here was an unweighted graph, है ना? All of you would agree to it that all the nodes here were unweighted, or we can say equally weighted at this point, right? And that is why the concept of finding the shortest path from a root node works perfectly well in case of a unweighted graph, right? But let's consider another case, right? I hope till this part it makes sense of how exactly you can find shortest path using BFS in an unweighted graph. But let's just take an example here of another type of a graph. Let's say the nodes are A. I'm drawing any random graph, and here let's say E, D, C and F. This is this. Right, the same graph that I have drawn, right? Here what I have simply done was, let's consider both the cases. This is going to be a weighted graph and this is going to be an unweighted graph. Let's see an unweighted graph as well. Right, let's say you have to find the distance, shortest distance between two nodes, that is A and F, right? And what your algorithm will simply give you is, it will give you a path very easily, and that is going to be this and this, correct? This is I think what the shortest path will be between two nodes at this particular point of time. And let's now consider the case. Let me take an example. Just give me a minute. Let me think of a scenario where we can work out this particular issue. Now let's say here I have 100, right? And let's say here I have 1, right? And this is also 1, right? Now what will happen is, if let's say the question remains same, right? The question remains exactly same, where you have to find the shortest path between A and F, and this is the, I would say, the cost, right? The cost. Now what you will what your algorithm will do is, it will follow the same scenario, right? It will say that this node is at level 0, this node is at level 1, and this node is at level 2. So the shortest path is going to be this path only, right? And what is the cost of this path? It is going to be 1 plus 100 is equal to 101. But do you think, was it the shortest path? Was it really the shortest path, or I had a better way to move? What do you think? Was there any way in which I could have reached F in a more, I would say, cost which was actually less than 101? Right. I could have very easily done that, right? I could have very easily done that. How exactly was? There were multiple ways. I could have used this path. I could have gone to B, I could have gone to D, and then I could have gone to F, right? And the total cost actually would have been 3. But you would have seen that if I would have actually used that particular case, right? If I would have used that particular case, this node at level 1, this node as level 2, and this node as level 3, right? But if you would have done that particular kind of a scenario, you would have seen that that makes the node F at level 3. So these would be the typical case, right? This would be the typical case where BFS will not work. Just give me a thumbs up first if this concept makes sense of how BFS will not work for weighted graphs. Is this part clear? That why exactly BFS is not going to work for weighted graphs, but it works perfectly fine for unweighted graphs, right? Yes. Ismail, yes, you can watch the video afterwards as well. The recording will be available. Alright. So the problem that we have recognized is the concept of finding shortest path works well with unweighted graphs, but for weighted graphs it does not work well, right? So what we'll do is, if I draw another graph for your better understanding, let's say I had 1, these are the nodes, I have 2, and I have 3, 4, 5, 6, 7, and 8. What I'm trying to do is, I'm trying to just represent edges by their length. So this this is the cost 1. Let's say this is 2, 1, 1, 1, and 2, and 2, right? And let's say this will be our source, and this will be our destination, right? If we'll go by the path of if we'll go by the logic of shortest path, right? Here, according to our I would say normal BFS, the answer will be 2 plus 1, that is 5, correct? But here actually the shortest distance is going to be 4. Why 4? If we follow this path, but this path is something that the BFS will never do, because BFS always touches the closest nodes first, right? So BFS will never go by this path, it will always try to take this path only, but that path is not correct, right? So what we concluded was that हम standard BFS तो यहाँ पे नहीं लगा सकते, right? We cannot apply standard BFS to solve this problem, right? Standard BFS can definitely not be applied to solve this problem, right? For both, I would say for this node that this was the source and this was the distance. अब यहाँ पे ना कुछ observations करते हैं, ठीक है, and उससे we will try to learn this concept. अब हम क्या देख रहे हैं यहाँ पे, बहुत क्लियरली सुनना, इट विल मेक एब्सोल्यूट सेंस द लॉजिक ऑल्सो. डेस्टिनेशन नोड क्या है 6, राइट. अब ऑप्शंस क्या है हमारे पास. फॉर नोड 6 ना, जो हमारी डेस्टिनेशन नोड है, 5 इज ऑल्सो अ पेरेंट, है ना, एंड 8 इज ऑल्सो अ पेरेंट, करेक्ट. 5 भी एक पेरेंट है 6 के लिए और 8 भी एक पेरेंट है 6 के लिए, राइट. बट हो क्या रहा है, बट सिंस 5 राइट इज एट द लेसर लेवल, इसका लेवल क्या है 1, इसका लेवल क्या है 2, यहाँ पे लेवल है 1, यहाँ पे लेवल है 2, यहाँ पे लेवल है 3. अब पॉइंट ये है क्योंकि 5 का लेवल कम है, ठीक है, बिकॉज 5 इज प्रेजेंट एट अ लेसर लेवल कंपेयर टू 8, इसीलिए द रूट नोड और आई वुड से द सोर्स नोड टचेज दिस नोड फर्स्ट एंड दैट इज वाई वी कम टू 6, है ना. यही हो रहा है. दिस इज द मेन रीजन वाई वी आर फॉलोइंग द येलो पाथ एंड नॉट द blue path. Why? Because the parent node here 5 is at the lesser level, that is why the BFS takes this path first, right. But can we do something? अब problem कैसे solve हो जाएगी यहाँ पे. The problem will be solved if 5 is actually not the node that the root node touches, instead it touches 8, है ना. What we can simply do is we can do something that this does not happen. कुछ ऐसा हो जाए that source node पहले 8 पे चले जाए, ठीक है, and then it goes to let's say 6 instead of first going to 5, correct. मैं क्या करूँगी, I will replace, what I will simply do is I will do a replacement where I will replace this edge, right. There is an edge 5,6 which has the cost 2, है ना, यहाँ पे एक edge present है with 2 edges. That means I will do this. So this was 5, ठीक है. I will introduce a dummy edge here D1 and D2 and यहाँ पे इसकी cost मैं 1 कर दूँगी, इसकी cost 1 कर दूँगी and I will get rid of this particular node, right. So I am basically inserting a dummy node in between. That means the node 5, 6, initially this looked like this. Now I have done this 5, D1, 6, 1 and 2, ठीक है. Is everyone able to see what exactly is happening here? And also I will do the same for this node as well. इसकी cost 2 थी ना, तो मैं यहाँ पे ना एक डमी नोड ले आऊँगी दोबारा, लेट्स से D2 है, और मैं कॉस्ट्स को ऐसे डिवाइड कर दूँगी, राइट. सो नाउ एग्जैक्टली हमारा रिजल्टेंट ग्राफ कैसा दिखेगा. हमारा रिजल्टेंट ग्राफ ना कुछ ऐसा दिखेगा. आई हैड 1, आई हैड 2, देन लेट्स से मैंने D1 बोल दिया इस नोड को, देन आई हैव 5, देन आई हैव 2, देन आई हैव 6. यहाँ पे भी हमारे पास वैल्यू क्या थी 2 थी ना, मैंने इसको भी डिवाइड कर दिया. अब बताओ, दिस इज द रिजल्टेंट ग्राफ. नाउ कैन यू सी आवर प्रॉब्लम विल बी सॉल्व्ड नाउ. व्हाट डू यू थिंक? नाउ डू यू थिंक BFS will work well? Now do you think BFS will work well when I have modified the graph in such a way that, don't you think essentially I have created this an undirected graph only? an unweighted graph when I have actually made the weights for all the nodes as equal, for all the edges as equal. I have essentially converted it into a, I would say, a unweighted graph, right? Now you will see here, now you will see that all the nodes are present at the right level, and now this is the path that we will take. Why this will be the path? Because this is at level 1, this is at level 2, this is at level 3, this is at level 4, this is at level 1, level 2, level 3. Now you will see here that both these nodes are now present at the same level, right? Let me just see if we missed out on any node, right? So now what will happen is, first I would say 1, right? 1 will go to this node and this node, right? Now will you apply BFS? They will go to both these nodes. Now they will go to both these nodes, and now 5 will go to D2, whereas 8 will touch 6 once, right? And the total cost of the path will be this only. What we have essentially done here is, we have modified the structure of the graph, right? We have modified the structure of the graph without changing any nodes. देखो हमने यहाँ पे किसी भी नोड को चेंज नहीं किया है, हमने बस इस ग्राफ को कन्वर्ट कर दिया है एक अनवेटेड ग्राफ में, right? This is what we have been done, and what the consequence of this was that the nodes have now been shifted to their right level, right? अगर हमें ऐसा गिवन था, अगर एक नोड है n1, एक नोड है n2 और उसकी कॉस्ट है 2, तो हमने बेसिकली उसको कन्वर्ट कैसे किया, n1 d1 1 और d1 n2 1, right? This is what we have done, right? So the overall, I think इससे हुआ क्या, one consequence was overall space बढ़ गई, the number of edges were increased, the number of nodes were also increased, right? But what we saw here was that now this is the conclusion that BFS can actually work for every random graph, ठीक है? Now with this solution, what we saw was there is no constraint now on the problem, be it a weighted graph or an unweighted graph, BFS can be applied in both the cases. पहले इतना बताओ, is this part clear? That how BFS can actually be applied to these problems in itself. Does this part make sense to all of you? No, Ismail, currently we are not that at point. Currently we are only considering the case when the weights is greater than or equal to 0. So that is again, I think, one constraint now also, that this case will only work when the weight is greater than or equal to 0. अच्छा, but अब देखो and try to look at this approach. Can you identify any issues? क्या इस approach में can you look for any issues? Somewhere where you think that this approach will be very tedious. Anywhere that you feel that this approach will not work, or even if it works, it is a very long process or very tedious one. एक बार देखो, try to look at this graph, see if you can identify any issues. Obviously this is going to work only for weights greater than equal to 0, so that is one case, but any other thing that you can identify? ऑलराइट, करेक्ट. देखो अब ऐसा होता है कि वेन एवर यू आर सॉल्विंग अ प्रॉब्लम्स विद ग्राफ्स, यहाँ पे तो सिचुएशन बहुत छोटी थी, राइट? either the weight was either 1 or 2, right? तो ज़्यादा I would say range नहीं थी, there was no range for weights. But consider करो a case that there is a graph in which there are weights, right? बहुत सारे weights present है and I would say the weights have a different value. Let's say the weights vary. Let's say they start from 1, 2, 3 and k. राइट नाउ व्हाट विल हैपन इज, आप क्या कर रहे थे, फॉर लेट्स से अगर एक नोड थी n1 और एक नोड थी n2 और यहाँ पे लेट्स से उनका वेट था 4, तो आप क्या करते थे, यू डिवाइडेड इनटू 3 पार्ट्स, राइट? आपने यू मेड 3 नोड्स. बट व्हाट विल हैपन इज, लेट्स अज्यूम करो जो वेरियंस है नोड्स का, राइट? जितनी वो वैल्यूज़ वेरी कर रही हैं, दैट वैल्यू बिकम्स k इक्वल टू 10 to the power 18, राइट? अज्यूम करो अगर ऐसा केस होता है, हाउ डिफिकल्ट वुड इट बी, राइट? आई जस्ट सॉ अभिषेक इज सेइंग दैट व्हेन द वेट्स आर टू बिग, देखो ये इशू नहीं है इफ़ द वेट्स आर टू बिग. लेट्स अज्यूम करते हैं वेट्स की वैल्यू ऐसे है 1, 2, 3 एंड लेट्स से दिस इज द ग्राफ, राइट? अगर वेट्स की वैल्यू ऐसे है, ठीक है, नाउ यू कैन सी हियर दैट द वैल्यू ऑफ वेट्स इज टू बिग, राइट? बट इट इज़ नॉट एन इशू. देखो यहाँ पे कोई इशू नहीं है, क्यों? क्योंकि मैं ऐसे कर सकती हूँ, राइट? आई कुड जस्ट डिवाइड इट, लेट्स से n1 and 1 and then c, राइट? मैं ऐसे डिवीजन कर सकती हूँ एंड आई कैन गेट द नोट्स टू बी एट द सेम लेवल. या फिर एक ऐसा लेवल अज्यूम करते हैं, जैसे यहाँ पे एक केस था 20,000, यहाँ पे था 10,000 और यहाँ पे था लेट्स से 40,000, राइट? ऐसे वेट्स थे. तो अब ये वेट्स की वैल्यू तो बहुत बड़ी है, राइट? बट इट इज़ नॉट एन इशू. मैं क्या कर सकती हूँ, ए और बी को ऐसे ही रख सकती हूँ, राइट? Then I can say 10,000 here and then I can say n1 and I can again say 10,000 and then I can have c, right? ऐसा मैं कर सकती हूँ and यहाँ पे d will remain same and यहाँ पे I can have n2 with the weight 10,000, I will have n3 with the weight 10,000, then I can have n4 again with the weight 10,000 and I can do this, right? This is not an issue. I would say अगर weights की value बहुत बड़ी है then it definitely not a issue, because यहाँ पे भी देखो we again converted it into I would say an unweighted graph. अगर सारे weights equal हैं then essentially it is an unweighted graph, right? That is not an issue. The issue will be if the variance is too big, right? What if the graph looked something like this, जहाँ पे एक वैल्यू 1 है, एक वैल्यू 10,000 है और दूसरी वैल्यू आई वुड से इज़ 35,000. अब इस केस में क्या हो गया, द वेरियंस इज़ टू बिग. नाउ दिस node or I would say this edge with a weight 10,000, it has to be converted into 10,000 edges of one node. हमें इसको 1 1 1 1 करके काफ़ी उसमें डिवाइड करना पड़ेगा. सो व्हाट द प्रॉब्लम इज़, द प्रॉब्लम इज़ नॉट द हाई वेट्स. High weights is not a problem. The variance of weights is the problem. For how many people does this make sense? That having high weights is not an issue. You can see here that is perfectly not an issue. Having, I would say, high variance of weight. When I say variance, you can see that we also have a node with weight 1 and we also have a node with weight 35,000, and that is a very big difference. And in those cases, actually applying BFS is very, very difficult, right? Clear to everyone? Perfect, right? सो यही एक सिनेरियो था, राइट. If anyone asks you what kind of issue BFS has, this is what you should be saying, that having big weights is not an issue. Having a high difference of weights between the nodes is an issue, and in those cases it is going to be a very tiring process to make that many nodes, because essentially the number of nodes increases and essentially the number of edges also increases, right, and it takes a lot of space in the memory, and it is not practically useful to solve problems like that. तो although हमने एक hack देखा of how we can solve this problem using BFS for weighted graphs, और वो work भी करता है, but वो ज़्यादा successful नहीं है. It is not a very successful way, right? So what we have in the picture is there are many algorithms, right? There are many shortest path algorithms which come into the picture now and help us find the shortest path between any two nodes. We have algorithms like Dijkstra's algorithm, we have Bellman-Ford algorithm, we have Floyd-Warshall algorithm. There are multiple algorithms जिससे हम ये जान सकते हैं what is the shortest distance between two nodes. We saw that BFS also works perfectly well. BFS can also solve this problem, but it only works well for unweighted graphs. The moment we introduce weights, BFS creates a problem, and we need some more optimized way to solve this problem, and that can be done by many different algorithms which are suggested by different mathematicians, scientists, and that can help solve this problem. Is this clear to everyone what we have discussed so far? I tried to summarize in a small picture. Clear to everyone? Perfect. Let's now move ahead and talk about these shortest path algorithms, right? We'll discuss कैसे ये work करते हैं, how exactly do they work. We'll dry run on a few cases and then we'll learn these concepts. All right. Okay, so we are now going to talk about a few shortest path algorithms. Right, we'll talk about a few shortest path algorithms, right? We'll talk about two today. We'll talk about Dijkstra's, we'll talk about Bellman-Ford after that, right? So I want you to listen to the concept very attentively. अगर कुछ भी doubt होता है, if you feel there's any point a particular part is not clear, please feel free to ask doubts regarding that part as well, right? How exactly Dijkstra's work, I'll explain that part in detail and we will see how it works. Right. So what we'll first discuss is going to be Dijkstra's algorithm, right? What we are trying to find here will be and how does Dijkstra work is, it helps us to find the single source shortest path between any two nodes. Okay, this is basically helpful to find a shortest path between any two nodes, right? And here when I say shortest path, okay, what exactly is the definition of that part? It basically means that the minimum number of hops required to reach from source to destination, right? So this basically helps us to take minimum hops to reach from source to destination, right? Another point here that is important will be that जो Dijkstra's algorithm होता है, it is very similar to BFS only, right? We do just small modification on BFS. It can be applied by using a small modification on BFS. अब एक एग्जाम्पल लेते हैं. then we'll try to learn it. एक बहुत ही important assumption है यहाँ पे, that Dijkstra's algorithms work only in the cases when every edge has a weight greater than or equal to 0. In only those cases does the Dijkstra's algorithm work. Alright, so let's say this is the graph. इसको 5 कर देते हैं. 10, 2, 7, 2, 1. Let's make this 3. Let's make this 5. Let's make this 2. राइट, ठीक है. तो हमें ये ग्राफ है और हमें शॉर्टेस्ट पाथ निकालना है, राइट. और हम क्या करेंगे, वी विल स्टार्ट आर BFS ट्रेवर्सल फ्रॉम S. ठीक है, ये हमारी सोर्स नोड है, हमने BFS ट्रेवर्सल S से स्टार्ट करा है, राइट. नाउ व्हाट विल हैपन इज, you can see here from S, right, from S you can directly go to B also and you can directly go from A as well, right. At this point I cannot say कि भाई S to A का shortest path 10 ही है just because S is able to directly reach both of them, right. I cannot simply say at this point कि भाई अगर हम S पे थे, अगर हम डायरेक्टली अगर A पे रीच कर पा रहे हैं और जो भी वैल्यू है पाथ की 10, दैट इज़ द शॉर्टेस्ट पाथ. वी कैन नॉट मेक दैट क्लेम हियर, राइट. इन ऑर्डर टू से कि भाई S से A तक का शॉर्टेस्ट पाथ 10 ही होगा, हमें ऐसा प्रूव करना है. यू नीड टू प्रूव दैट देयर एग्जिस्ट नो अदर पाथ जो कि शॉर्टर है ना. ये तो बहुत ही, आई थिंक दैट विल बी द वेरी बेसिक मैथ्स. अगर आपको ये प्रूव करना है कि S से A तक का शॉर्टेस्ट पाथ 10 है, तो आपको ये प्रूव करना पड़ेगा दैट देयर इज़ नो अदर पाथ विच इज़ शॉर्टर, राइट. इफ़ यू प्रूव दैट, दैट मीन्स आपकी वैलिडेशन सही है. बट इफ़ यू आर नॉट एबल टू प्रूव दैट, दैट मीन्स आपकी वैलिडेशन गलत है, राइट. सो आई कैन से इफ़ S to A, राइट, with the path with the cost 10 was smallest path between S and A, right, you need to be sure that no path exists between B to A, right. You have to prove at this particular point of time that no path exists between I would say B to A, or here if it is C, then I have to prove that no path exists between C to A of I would say path 10 minus weight of C, comma. How does this make sense to everyone? अगर मुझे ये प्रूव करना है कि अगर S to A का ये पाथ जो 10 है, इफ़ दिस इज़ द शॉर्टेस्ट पाथ, दैट मीन्स जो एक और पाथ था C to A का, राइट. मेरे को एक ऐसा प्रूव करना है, राइट. मुझे ऐसा प्रूव करना पड़ेगा कि जो भी S to C तक का पाथ है, ठीक है, दैट हैज़ टू बी ग्रेटर देन 9, बिकॉज 1 का तो पाथ था ही यहाँ पे, ठीक है. अगर मैं ये प्रूव कर दूंगी कि S से C तक का पाथ इज़ ग्रेटर देन 9, दैट मीन्स जो S to A तक का पाथ है, दैट विल बी द मोस्ट ऑप्टिमाइज्ड पाथ. फॉर हाउ मेनी पीपल डज दैट मेक सेंस? आई एम मूविंग वन नोड बैक. तो A को रीच करने के दो तरीके थे, एक तो S से तरीका था, एक C से तरीका था, राइट. नाउ इफ़ आई चूज़ द पाथ लेट्स से S वाला, ठीक है, और अगर मुझे क्लेम करना है कि S से ही शॉर्टेस्ट पाथ मिल रहा है, देन आई हैव टू मेक श्योर दैट C डज नॉट गिव द शॉर्टेस्ट पाथ, राइट. नाउ आई कैन सी हियर कि C to A तक की कॉस्ट अगर 1 थी, तो आई हैव टू प्रूव कि S से C तक मैं 9 कॉस्ट लूँगी या उससे ज़्यादा लूँगी, राइट? तो just by looking I can say that this should be the property that should be true, right? और यही underlying idea होता है, right? The underlying idea for Dijkstra's algorithm as well. हम हमेशा एक shortest node चुनते हैं and for Dijkstra's algorithm we will use a greedy approach. अब वो ग्रीडी अप्रोच हम कैसे लगाएंगे टू फाइंड द शॉर्टेस्ट पाथ? लेट्स से ये एक नोड थी, यहाँ पे उसमें मल्टीपल वेट्स थे, ठीक है? ये एक वेट था जो कि सोर्स से निकल रहे थे, ये एक वेट था, राइट? ये एक वेट था, ये एक वेट था, और एक ये वेट था जो कि मिनिमम वेट था आउट ऑफ ऑल दीज वेट्स, ठीक है? बहुत सारे वेट्स थे जो कि एस से प्रोपोगेट हो रहे थे, ये एक वेट था डब्ल्यू मिनिमम जो वेट था। तो हम क्या करेंगे, यू अप्लाई ग्रीडी अप्रोच। ग्रीडी में हम क्या करते हैं, अब हमें क्या करना है, हमें तो शॉर्टेस्ट पाथ देखना है, जो शॉर्टेस्ट पाथ होगा उसकी कॉस्ट सबसे कम होगी। तो व्हाट वी विल डू इज एट ईच पॉइंट out of all the options we will always choose that particular path which has the least cost, ठीक है? हम हर नोड पे जाएंगे in order to propagate to the destination and at each path हम वो नोड चूज़ करेंगे जिसका पाथ सबसे कम हमें उस वक्त दिख रहा है without caring about the consequences। ऐसा ही होता है अगर आप greedy approach लेते हो, if you are going to a destination, अगर आपके पास 3 रास्ते हैं, अगर आपको उनकी कॉस्ट 10, 20, 30 दिख रही है तो आप हमेशा 10 वाला चूज़ करोगे, उस वक्त एक ग्रीडी अप्रोच चूज़ करोगे विदाउट केयरिंग अबाउट द कॉन्सिक्वेंसेज। हो सकता है दैट पाथ फ्रॉम 10 इज एक्चुअली लॉन्गर इन द फर्दर डायरेक्शंस, बट टेकिंग अ ग्रीडी अप्रोच एट दैट पॉइंट आप 10 वाला पाथ चुन लोगे। सो हियर ऑल्सो मल्टीपल ऑप्शंस थे, मैं हमेशा मिनिमम अप्रोच लूँगी एंड यहाँ पे आफ्टर कमिंग टू ए यहाँ पे भी मल्टीपल पाथ्स होंगे, है ना, और कॉस्ट एड अप होती रहेगी। नाउ इफ़ आई एम मूविंग फॉरवर्ड, तो ये जो मिनिमम कॉस्ट थी एस से ए तक की आने की, प्लस अब आगे भी तो कॉस्ट होंगी ना, यहाँ पे एक और कॉस्ट है, यहाँ पे भी कॉस्ट है, राइट? यहाँ पे मल्टीपल कॉस्ट है, आप वो मिनिमम वाली कॉस्ट जो पीछे से आ रही थी उसको ऐड करते चलोगे एंड यू विल कीप मूविंग फॉरवर्ड, राइट? तो ये जो अप्रोच थी ऑफ ऑलवेज चूजिंग द मिनिमम पाथ आप हर नोड पे अप्लाई करोगे। You will apply at each and every step and build this greedy approach, right? Now आप क्या करते हो, हर nodes पे जाके you will take a step and that step will be the minimum weight at each level, right? So what we are doing is we are making greedy decision at each step, राइट? अच्छा, अब देखो हाउ इज़ इट मॉडिफाइड फ्रॉम बी एफ एस। आप बी एफ एस पे क्या होते थे, आप एक लेवल पे होते थे, आपके पास मल्टीपल लेवल्स होते थे, राइट? इन द नेक्स्ट लेवल यहाँ पे हमने क्या देखा था इन दिस एग्जाम्पल, लेट मी, अगर हम बी एफ एस ट्रेवर्सल लगा रहे हैं, राइट? अगर हम बी एफ एस ट्रेवर्सल लगा रहे हैं, अगर मैं इस नोड पे हूँ तो ये भी नोड लेवल 1 पे है, ये भी नोड लेवल 1 पे है, ऑल दीज नोड आर एट लेवल 1, है ना? बट यू कैन गो टू ईच एंड यू कैन गो टू एनी लेवल यू वॉन्ट, बिकॉज बी एफ एस कभी भी कोई डिफ्रेंसिएशन नहीं करता। जो छोटा सा डिफरेंस हम डाइस्ट्राज में ला रहे हैं वो यही छोटा सा डिफरेंस है कि अभी भी आपके पास एक नोड्स पे से मल्टीपल ऑप्शन है, आप कोई भी चुन सकते हो, बट द मॉडिफिकेशन इज आप वो पाथ चुनोगे जो कि सबसे शॉर्टेस्ट पाथ अप्लाई कर रहा है, ठीक है? एंड दैट इज़ द ग्रीडी अप्रोच। हम नॉर्मल बी एफ एस अप्लाई करेंगे, विल बी फॉर बी एफ एस हम क्या यूज़ करते थे, हम क्यू यूज़ करते थे, राइट? फॉर बी एफ एस वी यूज़ अ क्यू टू एक्चुअली इम्प्लीमेंट इट आइट्रेटिवली। अब हम क्या करेंगे, क्यू की जगह प्रायोरिटी क्यू यूज़ करेंगे। अब प्रायोरिटी क्यू क्या होती है, प्रायोरिटी क्यू में सारी वैल्यूज़ की एक प्रायोरिटी होती है। अब यहाँ पे हम हर नोड को एक प्रायोरिटी देंगे, एट प्रायोरिटी विल बी द लीस्ट आई वुड से वेट। तो जिस नोड या जिस एज का वेट कम होगा हम उस एज को चूज़ करेंगे। एंड हाउ टू चूज़ दैट एज, वी विल यूज़ प्रायोरिटी क्यू फॉर दैट। पहले जब हम नॉर्मल क्यू यूज़ कर रहे थे तो जो भी नोड फ्रंट पे होती थी हम उसको पिक कर लेते थे, बट यहाँ पे जिसकी कॉस्ट कम होगी हम उसको पिक करेंगे। एंड हाउ डू वी डू इम्प्लीमेंट दैट पर्टिकुलर सिनेरियो, वी डू दैट यूजिंग अ प्रायोरिटी क्यू, राइट? अब एक एग्जाम्पल ले लेते हैं, लेट्स टेक एन एग्जाम्पल हियर, ट्राई टू अप्लाई डाइस्ट्राज ऑन दैट and then we will work our example on that. Let me take an example here. एक नोड ले लेते हैं A, then I have B, and I have D, C and E, right? And let's say this is 4, 3, 1, 2, 2, 1, 4, 3, 5, ठीक है, ये है। और अभी वी हैव नॉट स्टार्टेड द BFS वाला ट्रेवर्सल ना, तो द अनविजिटेड नोड्स हियर विल बी A, B, C, D and E, right? These are the unvisited node and we start from A, right? If we start from A, तो currently A to A का distance तो 0 ही होगा, और अभी हमने कोई भी नोड बाकी ट्रेवर्स नहीं करी है ना, तो बाकी सबका डिस्टेंस विल बी इन्फिनिटी, राइट? नाउ व्हेन यू विल गो टू A, राइट, अगर आपने A को ट्रेवर्स कर लिया तो आप A को कट कर दोगे एंड यू विल सी द कॉस्ट फॉर इट्स नेबर। अभी तक A टू B जाने की कॉस्ट क्या हो गई है 4, राइट, और A टू C की कॉस्ट क्या हो गई है 2, बिकॉज दे आर डायरेक्टली एक्सेसिबल। तो करंट सिचुएशन को देखते हुए आई कैन से कि भाई A टू B का शॉर्टेस्ट पाथ 4 है और A टू C का शॉर्टेस्ट पाथ क्या है 2 है, ठीक है। नाउ वी विल मूव फॉरवर्ड, राइट, लेट्स से अब यहाँ पे मैंने क्या बोला था, वी ऑलवेज चूज द शॉर्टेस्ट नोड। अब ये वाली नोड भी लेवल 1 पे थी, ये वाली नोड भी लेवल 1 पे थी, बट यू आर गोइंग टू पिक दैट नोड जिसका लेवल कम है, तो मतलब मैंने ये पाथ चूज कर लिया, ठीक है। अब मैं C पे आ गई, राइट। नाउ द मोमेंट आई कम टू C, अगेन यहाँ पे मल्टीपल ऑप्शंस है, राइट। सो C टू E का शॉर्टेस्ट पाथ कितना है 5, और पीछे से मैं 2 ला रही हूँ बिकॉज दिस इज आर सोर्स, तो मतलब A टू E का शॉर्टेस्ट पाथ कितना हो गया 7, राइट। दिस इज व्हाट आई कैन से दैट A टू E शॉर्टेस्ट पाथ इज गोइंग टू बी 7, ठीक है। तो ये हमने देख लिया। अब A C D दैट मीन्स 2 + 4, मैंने क्या था, आप मिनिमम पीछे का वेट भी ऐड करोगे, राइट, आप पीछे का वेट जो ला रहे थे वो भी ऐड करोगे प्लस अपना वेट भी, दैट मीन्स हियर इट विल बी 2 + 4 6, दैट मीन्स फॉर D the shortest way as far as now is going to be 6, right, ठीक है। now we can see for B also आप क्या कर सकते हो 2 + 1, राइट, और अभी आपको कितना पाथ मिल गया 2 + 1 दैट इज 3, और अभी आपका वेट क्या था 4। जब भी आपको एक ऐसा आई थिंक वो मिल जाता है, पाथ मिल जाता है विच इज़ शॉर्टर देन द करंट पाथ, तो आप उसको अपडेट कर देते हो। मतलब सोर्स अगर A है तो शॉर्टेस्ट पाथ जाने की कॉस्ट कितनी हो सकती है 3, राइट। सो दीज आर द वैल्यूज दैट वी गॉट, ठीक है। अब यहाँ पे मल्टीपल ऑप्शंस हैं, आप C से कहाँ पे जा सकते हो, आप B पे जा सकते हो, D पे जा सकते हो, E पे जा सकते हो, 3 ऑप्शंस थे, राइट। बट व्हाट वी डू इज़ हम हमेशा मिनिमम वेट का ऑप्शन चूज़ करते हैं, राइट। वी ऑलवेज चूज़ द मिनिमम वेट ऑप्शन। सो व्हाट वी विल डू राइट नाउ इज़ we'll do that only, and यहाँ पे मिनिमम वेट किसका बना B का, बिकॉज B, D और E में आप देख सकते हो B का मिनिमम है, तो नेक्स्ट वैल्यू हमने चूज़ करी और हम आ गए B पे, ठीक है। तो हम A पे थे, C पे आए, अब B पे आए क्योंकि B का वेट था मिनिमम, तो हमने C भी ट्रेवर्स कर लिया, राइट। अब हमने B भी ट्रेवर्स कर लिया। अब देखते हैं B से क्या क्या ऑप्शन है। मैं B से D पे जा सकती हूँ, राइट। when I go from B to D, right, when I go from B to D here, what you will see is कि अभी तक D तक पहुँचने की कॉस्ट क्या थी 6, राइट, और B तक पहुँचने की कॉस्ट हमें ऑलरेडी पता है 3, तो 3 + 2 is 5, तो भाई हमें तो पहले 6 था, अब एक और ऑप्टिमाइज्ड मिल गया है, तो वी विल अपडेट इट टू 5, राइट। आई विल सिंपली अपडेट इट टू 5। नाउ हमारे पास B से E जाने का भी ऑप्शन है, राइट। अब B तक पहुँचने की कॉस्ट मिनिमम क्या है 3, राइट, 3 इज़ द मिनिमम कॉस्ट टू रीच B, तो E पहुँचने की कॉस्ट कितनी हो गई 3 + 3 6, राइट। सो ये भी एक ऑप्टिमाइज्ड वैल्यू हमको मिल गई है, तो वी चेंज इट टू 6, राइट। अब यहाँ पे B से C जाने का भी एक ऑप्शन है, तो B से आई वुड से B तक आने का ऑप्टिमाइज्ड ऑप्शन था 3, अब मैंने 3 ऐड किया तो 6, बट हमारे पास तो ऑलरेडी एक ऑप्टिमाइज तरीका है ना, वी कैन रीच टू C इन कॉस्ट 2, तो हम इस कॉस्ट को अपडेट नहीं करेंगे, राइट। अब व्हेन आई गो टू D, अब यहाँ पे क्या क्या ऑप्शंस हैं फ्रॉम B, मैं किस पे जा सकती हूँ D पे, ई पे, और सी तो मैं ऑलरेडी विजिट कर ही चुकी हूँ, राइट, सो आई कैन नॉट गो बैक एसेंशियली। तो यहाँ पे द मिनिमम कॉस्ट विल बी बेयर बाय डी, तो मैं डी पे आ जाऊँगी, ठीक है, बिकॉज ई की कॉस्ट 6 थी और डी की कॉस्ट 5 थी, तो आई विल गो टू डी नाउ। अब डी से देयर इज नो वेयर आई कैन गो, राइट, फ्रॉम डी आई कैन गो नो वेयर, राइट, सो आई विल नाउ मूव टू द लास्ट नोड दैट इज गोइंग टू बी ई हियर, राइट, बिकॉज बी एफ एस में अगर मैं लगा रही हूँ तो बी और डी के ऑप्शन है, तो जब बी हो गया नाउ वी विल गो टू ई। नाउ व्हेन आई कम टू ई हियर, राइट, नाउ व्हेन आई कम टू ई हियर यू विल सी कि ई से जाने का डी पे एक ऑप्शन है, बट ई तक पहुँचने की कॉस्ट क्या थी 6, और मैं डी पे जाऊँगी अगर यहाँ से तो कॉस्ट कितनी हो गई 7, विच इज़ नॉट गुड, क्योंकि मेरे पास तो एक 5 का ऑप्शन ऑलरेडी अवेलेबल है। सो दैट मीन्स आई कैन से इफ़ ए अगर आपकी नोड है, राइट, इफ़ ए इज़ द नोड, तो शॉर्टेस्ट पाथ कुछ ऐसे होंगे, इट विल बी ए, शॉर्टेस्ट पाथ सी तक का जाने का हो गया 2, फिर बी तक का जाने का हो गया 3 विच इज़ दिस, फिर डी तक का जाने का हो गया ये 2 जो हमने पिक किया था, और ई तक का हो गया ये पाथ विच इज़ 2 + 1 + 3। इज दिस क्लियर टू ऑल ऑफ यू? Just give a thumbs up if this whole part makes sense of how exactly BFS works, and बहुत ही small tweak करना है on the basic approach of BFS, and you can see that you can apply Dijkstra's. Plus, instead of queue, we are using a priority queue and solving our problem, right? Let's quickly take a look at the pseudocode here as well, right? A small pseudocode that I'll write, you can write for yourself as well for Dijkstra's. All right, let's quickly have a look. तो हमारे पास एक विजिटेड आ रहे हैं, राइट, एंड आई एम हैविंग अ प्रायोरिटी क्यू, जहाँ पे प्रायोरिटी इज़ डिफाइंड ऑन द सेंस ऑफ द कॉस्ट फॉर अ पर्टिकुलर पाथ, राइट। नाउ in this queue I am pushing something, right, and whatever I am pushing, अब I have इस queue में I am pushing a pair. What is that pair? 0, source, right. अब ये 0 क्या हो गया? This will be the distance, right, and this will be the node. तो currently अगर मैं start कर रही हूँ let's say यहाँ पे A पे, ठीक है, if I am starting from A, तो A का distance A से तो 0 है, and this is the node A that I will be passing here, ठीक है। Now till the time while the priority queue is not empty, right, till the time priority queue is not empty, so what I'll do is I'll quickly take the element which is at the front of the queue, I will pop it, right, I will keep the distance, so when I do top dot first, तो मेरे को क्या हो जाएगा, I will get the distance value, और जो नोड थी मुझे वो भी मिल जाएगी। दैट मीन्स अगर मैं ए पे थी तो यहाँ पे 2 ऑप्शन थे ना, 4 पाथ था, 2 पाथ था, तो मेरे को सी नोड मिल जाएगी, तो आई विल गेट समथिंग लाइक दिस 2, सी। तो शॉर्टेस्ट पाथ मुझे मिला 2 विच वॉज दिस, एंड मुझे कॉस्ट कितनी मुझे नोड कौन सी थी, सी, वो मिल गई, राइट। नाउ अब ये नोड विजिट कर दिए, तो वील मार्क दिस नोड एज विजिटेड, एंड सिंस दिस इसका शॉर्टेस्ट पाथ था, तो विजिटेड node equal to true here, right. Now I will go to its child, so for every child of this particular node, है ना, अगर अब हम C पे आ गए हैं, तो now we'll go to each and every child of C. Now if the child is already visited, right, if the child is already visited, तो आप कुछ मत करो, you simply continue, right? And what I am simply doing here is, in the queue I am pushing make pair, that is distance, right? Distance that is the already part of the parent node का जो भी distance था वो, plus the weight of the child, right? Plus the weight of the child and along जो node कौन सी थी वो थी child. This is what you have to do. This will be the entire supercode. बहुत similar है in reference to the BFS which we have already learned. The only difference is the I would say the priority queue that we are taking here. Rest everything is same. Is it clear to everyone? Hi Sumukh. Alright, perfect. So let's move forward to a different algorithm now, right? We've covered what Dijkstra's is. Now we'll cover the next shortest path algorithm, that is Bellman-Ford, right? But Bellman-Ford पर जाने से पहले the important thing we should learn is why do we require Bellman-Ford, है ना? अगर Dijkstra's एक already algorithm exist कर रहा था which was pretty efficient, it was giving us the shortest path as well, then why did we come up with another shortest path algorithm, right? अगर हमारे पास already एक shortest path algorithm है which is quite optimized, it works for every case as well, then what was exactly the need of coming with a new shortest path algorithm, right? अबे you are correct. So एक limitation होती है Dijkstra's algorithm की, right? That it only works for positive cases. I think मैंने ये बताया भी होगा पहले that हर edge का weight ना positive होना चाहिए. So I can say for Dijkstra's and there is a new algorithm, let's say Bellman-Ford, right? So this works well for positive weights, right? This also works well for positive case, but this does not work well with negative weights. अगर negative weights होंगे then Dijkstra's will not work, but this will work for negative as well, and both does not work for negative cycles. Right, so one of the use cases जो extra था Bellman-Ford में, that it was working well for negative I would say weights as well. और ऐसा क्यों हो रहा था? Because जो Dijkstra's algorithm है ना, it applies a greedy approach, right? Dijkstra's के अंदर हम greedy approach use करते हैं, जबकि Bellman-Ford के अंदर हम greedy approach use नहीं करते, right? Bellman-Ford does not use a greedy approach. और यही रीज़न था कि जो Dijkstra's की अप्रोच थी वो ना नेगेटिव वेट्स के लिए वर्क नहीं करती थी. लेट्स से अगर एक मैं एग्जांपल दूँ टू शो वाई Dijkstra's फेल वॉज, लेट्स से एक था ग्राफ ये S A B 3 2 and 4, राइट? लेट्स से दिस इज द ग्राफ और आपको ना शॉर्टेस्ट पाथ निकालना है between S to A, right? If you have to find the shortest path between S to A और आप normal Dijkstra's approach use कर रहे हो तो this will work fine और आपको shortest path मिल जाएगा between S to A, right? But अगर graph में ऐसा होगा that the graph is like this, right? Then Dijkstra's will not work, right? अब क्या होना चाहिए था? अब shortest path actually है ये 4 minus 2, right? But actually क्या होगा? Dijkstra's आपको path देगा ये which is wrong. क्यों? क्योंकि जो inherent approach थी वो ये थी कि आप हमेशा वो node choose करते हो जो कि उस वक्त सबसे आपको shortest path देती है. तो यहाँ पे क्या होगा? 3 था और 4 था, है ना? तो 3 और 4 में आप क्या चूज़ करोगे? 3, बिकॉज इसकी वैल्यू अभी छोटी है, राइट? तो आप क्या कर दोगे? यहाँ पे आंसर ए दे दोगे. सिमिलरली यहाँ पे भी आप 3 चूज़ कर लोगे एंड यू विल से कि शॉर्टेस्ट पाथ क्या है? 3. बट एक्चुअली शॉर्टेस्ट पाथ क्या था? 2, क्योंकि यहाँ पे अगर आप लंबा पाथ लेते और फिर यहाँ पे जाते तो आपको एक -2 की वैल्यू मिल रही थी, right? So that was the case where Dijkstra's fail, and Dijkstra's does not work for negative cases, right? Because यहाँ पे हम बहुत ही greedy approach यूज़ करते हैं, right? We use a greedy approach. हम उस वक्त सोचते हैं, we just look at the situation in hand and then we, I would say, then we take the decision, right? We do not care about the fact that अभी we are taking a greedy decision, but probably it will not be fruitful in the I would say later stages, right? So that was the case about Dijkstra, that was not working, right? So that is what we came up with. We came up with the idea of, I would say, Bellman-Ford algorithm, right? So let's just discuss that algorithm also. Here again the use case is same, that we can find the minimum distance between a source and destination, right? We can find the minimum distance between the source and destination, and it allows us to have negative weights, right? So this allows us to have negative weights also. अब जो underlying idea है ना behind Dijkstra's algorithm, it is something like this. Right, so this is the algorithm that we know. अब Dijkstra's algorithm क्या कहता है, which is actually correct as Bellman-Ford algorithm क्या कहता है, which is actually correct as well. अगर total number of vertices 5 हैं, ठीक है, अगर total number of vertices is 5, then what exactly does that mean is that जो maximum path होगा between any two nodes, it cannot exist, it cannot be more than v-1. This is what Bellman-Ford says, right? It what basically says was, if the number of vertices is 5, right, then the maximum path between any two nodes, right, जो maximum path होगा between any two nodes, it cannot be more than v-1, right? अब यहाँ पे देखो, यहाँ पे अगर मुझे S to D तक जाना है, right? So the number of edges is 1, 2, 3, 4, which is the maximum edges. अगर मेरे को इससे ज़्यादा वैल्यूज़ लग रही हैं, राइट, इफ़ आई एम टेकिंग मोर हॉप्स, राइट, इफ़ आई एम टेकिंग मोर हॉप्स एंड मोर एजेस, देन डेफिनेटली ग्राफ में साइकिल एग्जिस्ट करती है. फॉर हाउ मेनी ऑफ यू डज दैट मेक सेंस? दैट एट मोस्ट v-1 edges can be in one of our paths, right? And here this represents number of vertices. I'll repeat the concept once again, which is pretty simple. और वो ये कहता है कि अगर आपको किसी भी दो नोड्स के किसी भी एक नोड से दूसरी नोड पे जाना है, इफ़ यू हैव टू गो फ्रॉम वन नोड टू अनदर नोड, द मैक्सिमम नंबर ऑफ एजेस और द मैक्सिमम नंबर ऑफ हॉप्स इट कैन टेक इज इक्वल टू v-1. अगर आपको इससे ज़्यादा एजेस लग रही हैं, if it is taking more edges for you to go, then definitely the graph has existing a cycle, right? That means the graph has cycles in it path, right? If you take v or more edges in a path, if you take v or more edges for a path, अगर ऐसा हो रहा है, अगर आप ज़्यादा एजेस ले रहे हो, then definitely you will see here कि अगर मैं ऐसे यूज़ कर रही हूँ, S से A से B, then फिर से A, then this and this path. If I am using this path, then definitely there will be a vertex which will get repeat. If this is the case, then definitely I can say that there is a vertex which will be repeatedly I would say gone through, and that basically means अगर ऐसा है कि हम किसी वर्टेक्स पे दोबारा जा रहे हैं तो मतलब एक साइकिल एग्जिस्ट कर रही है, राइट. तो कॉन्सेप्ट ये कहता है कि अगर आपको एक नोड से दूसरी नोड में जाना है, द पाथ शुड बी सिंपल, देयर शुड नॉट बी एनी रिपीटेड एजेस, और वही जो पाथ होगा दैट विल बी द शॉर्टेस्ट पाथ, राइट. सो यू शुड ऑलवेज हैव अ सिंपल पाथ, राइट. द पाथ शुड बी सिंपल, मीनिंग दैट देयर शुड बी नो रिपीटेड एजेस. अगर देखो, अगर आप एक नोड पे फिर से जा रहे हो, राइट, इफ़ यू आर गोइंग टू अ नोड अगेन इन अ पाथ, दैट मीन्स आप कुछ एक्स्ट्रा टर्न ले रहे हो ना. अज्यूम करो इन अ रियल लाइफ सिनेरियो आप सोर्स पे थे और आपको डेस्टिनेशन पे जाना था, राइट. आपने क्या किया, आप यहाँ पे गए, आप यहाँ पे गए, आप यहाँ पे गए, ठीक है. तो शॉर्टेस्ट पाथ हमेशा क्या होगा, एक सिंपल पाथ होगा जिसमें आप एस से गए, फिर बी पे गए, फिर आप डेस्टिनेशन पे पहुंच गए. बट देखो, अगर आप ऐसा कर रहे हो, आप पहले क्या कर रहे हो, आप पहले ए पे जाते हो, फिर आप बी पे जाते हो, फिर आप सी पे जाते हो, फिर आप ए पे जाते हो, और फिर से आप जाते हो, तो डेफिनेटली ये पाथ लंबा है. अगर आप कहीं भी अपने पाथ में एक साइकिल ले रहे हो या फिर एक किसी नोड पे घूम के वापस आ गए, मतलब आपने लंबा रास्ता चूज़ किया है ना, यू चोज अ लॉन्गर पाथ फॉर दैट केस, एंड दैट इज़ द केस विच बेलमैन-फोर्ड सेज दैट दिस शुड नेवर हैपन, राइट. दैट इज़ द सिंपल फंक्शनैलिटी फॉर बेलमैन-फोर्ड. तो हम क्या करेंगे, we'll take an algorithm, right, we'll do it such a way that we'll apply the basic BFS kind of an approach, I would say not more than v minus 1 times, and then work on this concept, right. So ये this was the whole scenario of how Bellman-Ford is going to work, right. Let's quickly do a dry run, right, let's quickly do a dry run for Bellman-Ford as well. We'll take an example and we'll see how Bellman-Ford works for that scenarios. I'll just quickly show you the pseudocode first. And what here we have is, we have a graph, right. Again हमारे पास एक directed graph है, right. It will have weights also, ठीक है. vertices होंगी, vertex होंगी हमारे पास, edges होंगे, negative weights applied होंगे, बस negative cycles applied नहीं होंगी, right. So what you will simply do is, for all, I would say for all the edges, right, for all the vertex here, इनिशियली सबका डिस्टेंस जैसे हमने डाइस्ट्रास में किया था इन्फिनिटी होगा, राइट. और सबकी प्रीवियस वैल्यू, और आई वुड से द पेरेंट टाइप ऑफ अ वैल्यू विल बी नल, राइट. उसके बाद जो भी हमारी सोर्स नोड होगी उसका डिस्टेंस विल बी ज़ीरो. आफ्टर doing coming out of this for loop, the distance for the source will be made 0, and there will be a process which I will repeat v minus 1 times. That will be this. I will go to each and every edge, right. I will go to each and every edge और मैं वहाँ पे अपडेट कर दूँगी वैल्यू उस एज की, राइट. नाउ हाउ डज दिस अपडेट प्रोसेस वर्क्स इज, अपडेट प्रोसेस में क्या होगा, हमें एक एज मिलेगी, ठीक है. इन द अपडेट प्रोसेस वी विल सिंपली गेट एन एज. सो u कॉमा v रिप्रेजेंट्स एन एज. व्हाट आई विल डू इज, उस भी जो भी, दिस इज़ द, आई वुड से अगर a टू b है तो हम इसको a कॉमा b करके पास करेंगे, राइट. सो वट एवर डिस्टेंस दिस v विल हैव इज, दैट इज़ द मिनिमम डिस्टेंस ऑफ, आई वुड से v प्लस the distance of u plus I will say जो भी edge की length थी u comma v, right. I'll explain it to you. एक बार एक छोटा सा example ले लेते हैं. Let's quickly take an example of a graph here, then we'll come back to the whole code. So let's say S है, then we have an E, then we have D, let's say ये है, इसको A ले लेते हैं, -4, B, C, -2. So here I have negative weights also, 2, -1, 1, 8. This let's just keep it 1, right. सो दैट विल बी द केस. तो यहाँ पे टोटल नंबर ऑफ वर्टिस कितनी है, 1 2 3 4 5 6. सो वी हैव, इफ़ आई हैव 6 वर्टिसेस, तो टोटल मुझे 5 आइटरेशंस करनी पड़ेंगी, राइट. सो आई विल हैव टू डू 5 आइटरेशंस. लेट्स से इनिशियली S A B C D E. इनिशियली सोर्स का पाथ 0 हो गया, राइट. बाकी सबका जो अभी शॉर्टेस्ट पाथ है वो इन्फिनिटी है, विच इज़ सिमिलर टू व्हाट वी डिड इन डायस्ट्रा. तो अभी हम लोग फर्स्ट आइटरेशन कर रहे हैं, राइट. फर्स्ट आइटरेशन में हमें करना क्या था, हमें सारी आइटरेशंस करनी है, मतलब v-1 आइटरेशन करनी है. हर आइटरेशन में करना क्या है, आप सारी एज पे जाओ और वेट्स को अपडेट कर दो, ठीक है. तो अभी मैं सोर्स पे अगर थी, तो मैं अगर यहाँ पे आ गई हूँ, तो इसका वेट, e का वेट कितना हो गया 8, और इसका वेट कितना हो गया 10, है ना. दिस विल बी द सिंपलर वेट, और मुझे हर एज पे जाना है. तो मैंने s के लिए काम कर लिया. अब मैं a पे आ गई हूँ. अब इफ़ आई एम एट a, ठीक है, a से मैं कहाँ कहाँ जा सकती हूँ, c पे जा सकती हूँ और d पे जा सकती हूँ. तो c पे जाने का वेट कितना हो गया, कैन एनीवन टेल मी. दिस विल बी 10 + 2, है ना. दिस शुड बी 12 हियर. तो c तक जाने का कितना हो गया, 10 + 2 दैट इज़ 12. d पे जाने का पाथ वेट कितना हो गया, दैट इज़ 6, राइट. तो ये हो गई हमारी, आई थिंक, फर्स्ट आइटरेशन हियर. लेट्स नॉट डू दिस, एक काम करते हैं, लेट्स डू दिस. सो टेक्निकली हम लोग अभी d पे नहीं पहुंच रहे हैं. सो लेट दिस बी इन्फिनिटी ओनली, राइट. नाउ आफ्टर a आई विल गो टू b, राइट. अब जब मैं b पे आ गई हूँ, तो b से वेयर कैन आई गो, आई कैन गो टू a, राइट. आफ्टर लेट्स से आई एम एट b ना, तो व्हाट आई एम डूइंग इज, आफ्टर कमिंग टू a यू कैन सी कि मैं यहाँ से आई कैन नॉट रीच एनी पर्टिकुलर नोड, राइट, जिस पे मैं ऑलरेडी गई नहीं हूँ. सो आई सिंपली मूव फॉरवर्ड. फॉर c, राइट, यू विल सी कि c से आई कैन गो टू b. तो अब तक c का पहुँचने का पाथ इज ऑलरेडी नोन. b पे मैं कुछ कर ही नहीं सकती थी, बिकॉज b का पाथ ही अभी इन्फिनिटी है ना. तो आई सिंपली मूव्ड फॉरवर्ड. जब मैं c पे आई, तो c का पाथ तो मुझे 12 पता है, तो c से b पहुँचने का पाथ कितना हो गया, 10 एट दिस पर्टिकुलर पॉइंट ऑफ टाइम, है ना. एंड नाउ मैं d पे आ गई. अब d पे कुछ कर नहीं सकते, बिकॉज d का पाथ इज स्टिल इन्फिनिटी. नाउ आई कम टू e, राइट. नाउ व्हेन आई कम टू e, e तक पहुँचने का पाथ वॉज 8, सो e टू d का पाथ विल बी 9, राइट. सो दिस इज वॉट आई गेट इन द फर्स्ट आइटरेशन. अब इसके ऊपर सेकेंड आइटरेशन करते हैं. S A B C D एंड E, राइट. एंड अभी तक वैल्यूज़ क्या थी, 0 10 10 12 9 8. अब हम सिमिलर आइटरेशन दोबारा करेंगे. अब S जब व्हेन वी वर एट S, तो वी सॉ हम कुछ अपडेट नहीं कर पा रहे हैं, बिकॉज अभी तक स्टिल E और A तक आने का पाथ इज सेम, दैट इज़ 10 and 8. अब व्हेन आई एम एट A, ठीक है, A से C तक का पाथ विल स्टिल बी 12, सो नो अपग्रेडेशन हियर एज वेल. व्हेन यू गो टू B तक ऑल्सो देर इज़ नो अपग्रेडेशन. C पे भी देर इज़ नो अपग्रेडेशन. अब D पे देखते हैं, ठीक है. व्हेन यू वर एट D, तो यहाँ पे वॉट वी सॉ वॉज, D से हम कहाँ पे जा सकते हैं, -4 पे, एंड मतलब A और C पे जा सकते हैं, है ना. अभी तक D तक पहुँचने का पाथ क्या था, 9. अब D से A तक पहुँचने का पाथ विल बी 9 - 4 विच इज़ 5. पर हमें क्या पता है, 10, विच इज़ रॉन्ग ना. मैंने यहाँ पे इसको अपडेट कर दिया 5. अब C तक पहुँचने की कॉस्ट हमें कितनी पता है, 12. बट 9 - 1 कितनी होती है, 8. तो मतलब C तक पहुँचने का भी एक ऑप्टिमाइज्ड तरीका हमको मिल गया है, राइट. सो आफ्टर 2 आइटरेशंस, दिस इज़ वॉट द फाइनल एरे विल लुक लाइक, और फाइनल डिस्टेंसेज विल लुक लाइक, ठीक है. सिमिलरली इफ़ यू डू दिस फॉर सेकेंड आइटरेशन, राइट, and you will update these cost simultaneously, what you will see is, तो हमने अच्छा वी हैव डन 2 आइटरेशंस. तो पहली आइटरेशन ये थी, सेकेंड आइटरेशन ये थी. फॉर द थर्ड आइटरेशन जो हम करेंगे, 0 5 10 8 9 8, राइट, ये हमारे पास कॉस्ट प्रेजेंट थी, राइट. व्हाट यू विल सी हियर इज, जब हम A पे थे, राइट, व्हेन वी वर एट A, अब A तक पहुंचने की कॉस्ट क्या थी, 5, जो कि हमने अपडेट करी थी. अब A से C तक पहुंचने की कॉस्ट कितनी हो गई, 5 + 2 7. बट हमें कितनी पता है, 8. तो मैंने इसको अपडेट कर दिया 7 पे, राइट. सो दिस इज़ व्हाट विल हैपन. अब अगर मैं C पे आई हूँ तो C तक की कॉस्ट अपडेट होगी. अब तो 7 हो गई है, राइट. नाउ फ्रॉम गोइंग टू C टू B कॉस्ट कितनी हो गई? 7 - 2 विच इज़ 5. और हमें कितनी पता है? 10. तो यू विल अपडेट दिस कॉस्ट, राइट. एंड हाउ लॉन्ग विल यू कीप डूइंग दिस प्रोसेस? आप ऐसे 6 आइट्रेशंस करोगे. एंड वॉट यू विल सी इज दैट आफ्टर 6 आइट्रेशंस, right, after 6 iterations, this is what you will get, that the minimum path from for source to source is 0, for source to A is 5, for source to B is 5, then 7, then 9 and 8, right. और आपको कितनी बार ये प्रोसेस करना है? You have to do I think 5 iterations for this, क्योंकि टोटल नोड्स थी 6. सो आफ्टर 5 iterations आपको हर नोड के लिए शॉर्टेस्ट पाथ मिल जाएगा, इवन इफ वी हैव नेगेटिव वेट्स. डज दैट मेक सेंस टू एवरीवन? हाउ एग्जैक्टली यू आर गोइंग टू लर्न बेलमैन-फोर्ड? बहुत ही छोटा सा डिफरेंस था अगेन हियर, दैट वी आर अप्लाइंग द सेम डाइस्ट्रास वाला कॉन्सेप्ट, बट हम एक फिक्स नंबर ऑफ आइट्रेशंस के लिए लगा रहे हैं. और उससे प्रॉब्लम क्या सॉल्व होती है? इट सॉल्व्स द प्रॉब्लम ऑफ नेगेटिव वेट्स. Now Bellman-Ford is what we know is best as of now, and it can work for positive weights also and negative weights also. Is everything clear what we discussed in today's class? I think we covered a lot of things today. हम लोगों ने cycle detection पढ़ा. We learned how cycle detection works. We learned how BFS works and how it can help to find shortest path. फिर हमने डिस्कस किया व्हाट आर द शॉर्ट कमिंग्स ऑफ BFS, वेयर एग्जैक्टली BFS विल नॉट वर्क, व्हाट वर द इश्यूज विद BFS. देन वी कम अप विद सम शॉर्टेस्ट पाथ एल्गोरिथम्स, दैट इज डाइस्ट्रास, एंड वी केम अप विद आई थिंक बेलमैन-फोर्ड एज वेल. डाइस्ट्रास के हमने कुछ डिसएडवांटेजेस देखे, राइट. वी सॉ सम डिसएडवांटेजेस फॉर डाइस्ट्रास एंड देन वी केम अक्रॉस विद द अदर सिनेरियो. आकाश, आई कैन नॉट थिंक लाइक ऑफ अ रियल केस सिनेरियोस, राइट. अगर आप ऐसे रोड्स एंड पाथ के केसेस में एग्जिस्ट करोगे, देन डेफिनेटली आई कैन नॉट थिंक फॉर नेगेटिव केस, बट देयर विल बी अ यूज केस, अ रियल लाइफ एप्लीकेशन वेयर यू कैन सी नेगेटिव वेट्स विल बी यूज्ड. बोथ आर फाइन अभे, बोथ वर्क्स परफेक्टली फाइन. यू कैन यूज एनी if you want. Yes, Vishnu, we did find the minimum path only. Just give me a second, I'll show you. यहाँ पे देखो, in Dijkstra's जो फाइनल आंसर था, राइट, इन द फाइनल आंसर द डिस्टेंस फॉर A to A was 0, right. The distance for A to B was 3 minimum, for C was 2, for D was 5 and for E was 6, right. So it was working on both the cases. Yes, Abhishek, it will work, but यहाँ पे भी you'll have to take care of that parent situation, because eventually Bellman-Ford, Dijkstra दोनों में हम BFS ही लगा रहे हैं, right. You will have to take care of that part. Otherwise, we should be good to go, right. So if the session was useful to all of you, right, we'll end our series here on graphs. I hope the session was useful. You were able to learn concepts. I know we did not, like, I tried to cover all the things in a very efficient manner, in any very precise way, so that it becomes a good learning material for all of you and a revising material for all of you, which you can just come across anytime you want. So I hope it was helpful. If you want to learn in a more detailed manner, we definitely have some courses on Unacademy which you can use. I'll quickly show it to you as well. So you can just go to unacademy.codechef.com. तो हमने जो लर्न किया था अभी, राइट, वट एवर वी लर्न, जस्ट गिव मी अ सेकेंड. Right, so what we learned was actually a small micro course. If you want to learn everything in detail, so we have a lot of courses. आप देख रहे हो, there is a course dedicated for just trees and graphs, जिसमें at least we have 8 to 9 lectures, and there is like a 2 stretch graph. So if you want, this is something that interests you, if you want to learn this way in a more, I would say, optimized manner and in a more detailed manner, you can definitely go ahead and take the subscription. There are multiple courses like you can see here on the screen, right? I have been taking a lot of courses as well, and multiple instructors have been taking them as well, right? So we have, let's say, you can see here that we have 2 courses on graphs. We have a course on trees and graphs, which contains alone 7 to 8 classes. Then we have another course on graphs too, right? So if this is something that interests you, you probably want to go ahead with, you can simply go to get subscription, right, and click on get subscription here, and you can take. If you want, you can use my referral code, which will be helpful for you here, and you can get discounts, right? This is something just I wanted to put it out there if you feel something that is useful for you. Otherwise, you can always tune in to these classes as well, right? So thank you everyone for attending. I hope I was able to make 2 hours of this class today useful for you, and I will definitely be back with more courses, more micro courses on different topics, and we'll meet there again, right? Thank you everyone. Thank you, Abhay. Bye bye.